Okay, in this lesson, we're going to be talking about two new proportions or formulas we're going to be using. These are not necessarily in the context of similarity. They're just two other scenarios where you guys would use proportions to solve. So the first one is called the side splitter rule. It says that if multiple parallel lines cross two transversals, the segments of the transversals are proportional. Okay, so the picture that I had over here illustrates that. So it has to be multiple parallel lines. So that means more than two. So we're usually going to have three. They need to be either clearly marked or have angle relationships that show that they're parallel. So 1, 2, 3, and then two transversals. And these four segments that we have kind of created in this diagram, those are proportional. So you would have A over B, the two segments on this transversal are equal to the two segments on this transversal written as a proportion. Now for this one, you guys can write the proportion in whatever order you want on this transversal. You could even start on this one if you wanted to. You just have to make sure that whatever pattern you use, you have to go in the same direction for the other transversal. So see how this one, when they wrote the ratio, they went top down, and then they did top down on this one too. You could also go bottom up. You could do B over A equals D over C. You could even start on this side if you wanted to. C over D equals A over B. Again, it doesn't really matter as long as you maintain the pattern for both sides. So to illustrate, we have an example here. They're telling us that this segment is 9, this segment is 15, this segment is 11. We're trying to find this one, so I'm going to write X. Now in the past, when we were writing proportions, before the right triangle stuff, the pattern that we used for writing proportions was to start with a variable. So that's what I'm going to do. I'm going to tailor the way that I write the proportion, all right, up here by starting with the variable and just making sure I use the same pattern on the other transversal. So I'm going to go bottom up on this transversal, so X over 11, which means I have to go bottom up on this transversal, which is going to be 15 over 9. All right, once you have it set up, you cross multiply, so you'd have 9x equals 165. And then just math really quick, that would be 18.3 repeating. Okay, so it's as simple as that to use a side splitter. You just pick where you want to start and just make sure you mimic the same pattern on the other transversal. In many situations it will work to go sideways like this, but we want to stay true to the proportion here and just use the segments along one transversal and then switch to the other instead of going over the empty space here. It'll just help maintain the traditional way that we're doing the proportion over here. But oftentimes you will get the same answer if you kind of go sideways too, but sometimes you don't. All right, so over here we have the same situation, except they've given us 8, 9x, and then instead of giving us this little piece separate, they've told us what the whole length is. This is really the only wrench they could throw at you to make the situation more difficult. It's either everything's given to you up front, or you have to figure out one or more of the pieces yourself. But we have enough information to put a label here. If this is x and the whole thing's 20, that means that this little piece is 20 minus x. So that's something you may have to do in the future, is check to see if you have all four of the little segments, and if you don't, just do a little manipulation so that you do. So for this one, I'm going to go ahead and start with this label and go this way, which means I'm going to do the same thing for this transversal. And again, you can tell it's a side splitter because we have 3 parallel lines, 2 transversals. So I'm going to start here, and again, you get to choose wherever you want to for our purposes. And I don't have the answer key in front of me, so I'm not sure if I did this on the printed answer key for those of you who have that. So the 20 minus x over x, and then the 8 over 9. And then I would cross multiply, so I get 180 minus 9x. Excuse me, equals 8x. I would add the 9x over, so 17x, and then I have to divide 180 by 17, and you would get 10.6 rounded. Okay, so that's basically how you use the side splitter proportion to solve. Another way you can use a side splitter is to actually set up a proportion rather than solve it. So in this one here, we're just looking to finish the proportion, find the pattern that they're establishing here, because they could do all sorts of different patterns. They could match small to small, medium to medium, stuff like that we've seen in the past. They could just do an arbitrary pattern of different segments and you have to match that on the other transversal. There are a lot of different ways that they can create patterns and proportions here. Especially since the transversals are crossing to create that triangle shape, there's a lot more flexibility they have there too. So we're just going to take a look and see if we can figure out these proportions. So the first one over here, I'm going to use color coding to illustrate. So I'm going to highlight the parts that they gave you. So they have B, D, and then DF. So these are two segments on the same transversal here and here. I don't know this piece, but I know the second piece is EG. So clearly, to mimic the same pattern on this transversal and this transversal, I would need this piece right here, which is going to match up with that part. So I would fill in with CE. Okay. For the next one, I have AD and BD. So I have this full section and this little part that's overlapping. And then I have AE, and we're trying to finish that pattern. So clearly I have these two, but I need the corresponding part to that on this transversal, which is clearly CE again. Okay. Now this next one is a little bit more abstract. So for this one I have DE, which is a section of one of the parallel lines, compared to FG, which is a section of another parallel line. And then they're comparing that to AD. Okay, so this is kind of interesting. Hopefully you see that with the parallel lines, the way that the transversals are kind of angled, we have a short, medium, and long parallel line. They're labeling the medium and the long. And then they're comparing that to segments along this transversal. They've given us AD. If you notice, look really carefully, we have little chopped up pieces between the B, the D, and the F along this transversal. From A to B is the shortest segment. If you go from A to D, that's the medium, and then A to F is the longest extension you could go along the transversal. You can even see it in triangles. Hopefully you guys can see right here, this triangle right here, and then this bigger triangle right here. You can kind of see that. I'm trying to find the bottom and the side of one triangle compared to the bottom and the side of another triangle, if you think about it that way. So in this ratio, they compared the bottom of this triangle to the bottom of this triangle. Now we're comparing the sides. So I have the side of this triangle compared to the side of this triangle, which would be AF. So there are two different ways of thinking about it. You can use the medium and long of the vertical parallels, or you can do the medium and the long of these segments along this transversal. Or you can use the triangle trick. That's the other way you can look at it. And this last one is AB and DF. So we have the first and third segment along this transversal matched up with blanked EG. So I need the first segment here to fill out that pattern, the AC. Okay. So you can use pattern finding there as well to fill out proportions in different aspects within the picture. The second thing we're going to talk about is the triangle angle bisector theorem. So this says that a ray that, here I'm going to type this actually. A ray that bisects an angle of a triangle cuts the opposite side, so that's the side opposite the angle, cuts the opposite side into two segments so that the segments on either side of the ray are proportional. Okay. So basically, if, and you need to have this information in the picture, I didn't add it there because I wanted you guys to do it by hand. If the directions say that a ray is a bisector, or you already have markings in the picture that have this angle is congruent to this angle, that's the only time that you can use this rule. This is not similarity. All right, we can't guarantee that this triangle created right here is similar to this one, or that they're similar to the full triangle. We don't know that. We don't have enough information. But in this particular scenario, and it works for every triangle, if you draw an angle bisector out like this, these two, the side segments on one side of the bisector stacked as a ratio are congruent to these segments on the other side of the angle bisector stacked as a ratio. So these two as a fraction equal these two as a fraction. Okay. Now again, you don't want to jump across the picture. You shouldn't compare this to this and that to that. You want to stay on one side of the one side of the bisector and then switch to the other when you're writing your proportion. So this example is already set up for us. In the diagram, it says that XY bisects ZXV. So there's your permission to use this rule. If you didn't know that, you couldn't do this. So because it's an angle bisector, I can take these two objects and write them as a ratio set equal to these two as a ratio. So I'm going to start with the variable like we have in the past, and again, whatever pattern you do on one side, you just do on the other. So I'm going to go from a to 5, so a over 5. And then mimicking that same pattern, bottom up, I'm going to do 20 over 25. Notice how I stayed on one side of the bisector and then switched to the other. So you cross multiply, you get 25a equals 100. When you divide, you get that a is equal to 4. Okay? And then this one, again, another example in the diagram, CAD is congruent to DAB. So there's your angle bisector kind of indication there. AB is 15. ABC is 9. And then they tell you 9. There we go. They tell you that this is 14. They want to know the length of DC. Now remember, just like in the side splitter question that we had up here, we had 1, 2, 3 of the segments labeled and not the fourth one. That's the same thing over here. We should have 1, 2, 3, 4 segments labeled. We have 1, 2, 3, and then not this one. We don't have a specific label for that. So we're going to take the information that we do know because they gave me this section, or I called it X because that's what we're looking for, and they gave me the full length. So to fill in the information that I need, I'm going to call this 14 minus X. Again, this is really the only wrench that they could throw at you to make it a little more complicated. So just make sure you know how to address that if you see it. So again, I'm going to use the rule that I saw up here to solve. I'm going to start with this expression again, and I'm going to go up like that. So I would have 14 minus X equals over 15. Because I went bottom up on this side, I'm going to do the same thing here. So then it would be X over 9. I'm going to cross multiply. Oops. I get 126 minus 9y is, X is equal to 15x. I'm going to have to add that over. No, sorry. I wrote that as a 5 instead of a 15. There, okay. So that's 24x. So when you divide 126 by 24, we get 5.25. Oh. Alright, so that is a pretty straightforward application of either of those two rules. Alright, this last page of the notes here, this is our cumulative solving practice. So I didn't just put a bunch of practice of side splitter and angle bisector here, because on the test, all the solving questions are going to be jumbled together. So I want to make sure that you guys are capable of looking at a question and knowing what strategy to use to solve. So this is a cumulative review. It has stuff from our very first and second lessons where you had just your similar triangles and setting up proportions using corresponding sides. You have nested diagrams, you have the right triangle stuff with splash mountain and roller coaster rule, and then we also have stuff from today's lesson with the side splitter and the triangle angle bisector. So you really just have to go through at these examples, figure out which one it is, and then move forward with the strategy you want to use. So this first one, this is from our first and second lesson, kind of. We have similar triangles here, and we can tell they're similar because of the parallel lines. They gave us alternate interior. We also have vertical angles right here. So by angle, they're similar, right? So I can use similar triangles. You should remember that the definition of similarity includes the fact that corresponding sides are proportional. So we're going to match them up. We can use the markings to know what's corresponding to what. So clearly this side right here between the double and the single corresponds to this side, which is between the double and the single in this triangle. So to write my proportion, I know that 2x and 10 are corresponding, so they will become one of our ratios. And then make sure you go back to the triangle that this came from. So 3x minus 7, that corresponds with 9. And then you would cross multiply. You're going to subtract that over. And then divide. Oopsie. Negative 70 divided by negative 12 is 5.8 rounded. Excuse me. All right, so that was the first one. Now this one, we look a little bit closer, and we notice that we have this angle is congruent to this one. So these are not similar triangles. We don't have angle, angle. We can't find side, 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 or side, angle, side. We don't have information to say that these are similar, and we don't have to, because hopefully when you see angle is congruent to angle, you can remember immediately the triangle angle bisector theorem. So this is an angle bisector, so that means these stacked are equal to these stacked. I'm going to start with the variable and go up and make the same pattern here. So a over 3 is equal to 6 over 4. You don't have to draw those arrows if you don't want to, in case it might confuse you with Splash Mountain. I just like to do that to remind myself of what direction I'm going in. Excuse me. Cross multiply, we get 4a is equal to 18. 18 divided by 4 is equal to 4.5. Right, we take a look at the next one. We notice it is a right triangle with an altitude drawn inside. That is specific to our lesson 3, I think it was, with the Splash Mountain roller coaster rule. That's exclusively for right triangles. So when you see that right triangle with the altitude drawn, you have to think of one of those two methods. The altitude is not labeled, it's the leg in this scenario that's labeled, so that's the roller coaster. So you start as far away as possible. You always start going across the hypotenuse, loop the leg, and then land on the piece adjacent to it. Then I follow that track to write the proportion. So this section right here is the full hypotenuse x plus 2. And then over 3. And then 3 over 2. And cross multiply 2x plus 4 equals 9. I subtract the 4, that gives me 5. Divided by 2, I would get 2.5. All right. So hopefully you guys were able to kind of tackle those fine by looking at what scenario it was, how to write the proportion, and you should have been able to just move forward from there successfully, I hope. But we have a couple more examples here. So when you take a look at this one, you'll notice that we have 3 lines and then 2 extras right here. So this looks like a side splitter, but don't rush. You need to make sure that these lines are parallel. If you take a look, they gave us these little markings here that stand for congruent angles. Those are all corresponding. Congruent corresponding angles gives us parallel lines. So even though they didn't give us the symbols, they give us the angles to show that they are parallel. So this is indeed side splitter, 3 parallel lines, 2 transversals. So I'm going to use the segments of one transversal and then use the segments of the other transversal. Again, I'm going to start with my variable and go this way. So x over 9. I'm going to do the same direction over here. I'm going to start back at the 3 and then go forward to 3.5. And then cross multiply. 3.5x equals 27 is 7.7 rounded. Okay. This next one only has 2 parallel lines, so we're not going to try to use side splitter here. Remember, when you have this kind of scenario, this is actually a nested diagram when you have one triangle inside of another. So this is the one where you're going to draw them off to the side and then match up corresponding sides. So I have the small triangle. That's horrible. Try that again. Boom, boom, boom. And that's a little better. And then we have the bigger triangle like this. And then I know that the sides are 3 and x for the little triangle. The bottom for the big triangle is 16. And then I have to add these together to get the side, which is 8. So now once you have them all separated, it's already set up with everything corresponding. So x over 16 equals 3 over 8. Let's multiply 48. Let me double check that. Oops. Yeah, 48. And then you divide 48 by 8, you should get 6. Just jumping ahead, said what the answer was instead of x. All right, so again, when you see a small triangle inside of a bigger one, that is your nested diagram. And so that's actually happening with this one too. We have a small triangle right here inside of a bigger one. Again, this is 2 parallel lines, so we want to avoid using side splitter just so we don't get the the process is messed up. So we're just going to stick with the method that we've been using along so we don't confuse them. So I have the bigger triangle, and then I have the little one. So this is 18, this is 12, the bottom of the bigger triangle is 16, and then this side is going to be A plus 18. To add those two segments together. Again, they're set up in corresponding relationship already, so I'm going to start with my variable expression. A plus 18 over 18 equals 16 over 12. And then you cross multiply. 18 times 12 is 216. And then 18 times 16 is 288. So for this one, hopefully you guys can see, you would subtract the 216, divide by 12, and you would get 6 again. All right, so there's two nested diagrams. This is also a nested diagram, right? We have a lot of practice with nested diagrams. So you need to make sure that you notice that you have the small triangle and the bigger triangle. You can sometimes do this in your head, but I feel like it's probably a better idea to just draw and relabel. So we have the x and the 4, and then because we already have an x and then a second x, when you combine them, just go ahead and combine like terms. So it'd be 2x plus 1, and then along here is 10. So again, you're going to set up using corresponding sides. So I have x over 2x plus 1 is equal to, go back to the original triangle, 4 over 10. So you're solving like this. Make sure you guys don't forget, if there are two objects and you're multiplying across multiplication, you need to make sure you distribute to both. That's a really common mistake to make, so you guys got to be really careful. It's 4 times 2x and 4 times the 1, so you need to make sure you get both of those there. So then you subtract so that the x's are on the same side, and then you divide, you get x is equal to 2. Okay. Now this next one here is different. So this one, again, it's a right triangle with an altitude drawn inside. That is either going to be Splash Mountain or the roller coaster. The altitude is the one that's labeled. So this is going to be Splash Mountain with your arrows guiding you. In order to do a Splash Mountain, you need to know this section and this section separately. They've given us this and then told us that the whole length is 11. So you have to do a little bit of quick side work. So if the whole thing is 11 and this is 5, that means that this is 6. So I need that number in order to write the proportion. So it's going to be x, dang it, 6 over x equals x over 5. Follow the arrows that you drew. Or you can just memorize the proportion, that's fine too. And then we cross multiply, so x squared is equal to 30. 30 is not a perfect square, and it can't be simplified once you put it into a square root. So you're just going to write square root of 30, and that would be your answer. Okay. This one, again, you take a really careful look. You notice that we have two congruent angles right here. That makes this an angle bisector. So we're going to be using the angle bisector rule we learned today. I'm going to start with my variable, so x over 4. We do the same pattern on the other side, so that'd be 7 over 3. So 3x equals 28. 28 divided by 3 is 9.3 repeating. Right? This is another side splitter. We have 3 parallel lines, 2 transversals. So we're going to be using the side splitter rule, which means I need 1, 2, 3, and then 4 sections. This is currently blank. So this is like the second example we saw when we introduced this rule. They told me the full length and then part of it, but not specifically what this was. So I'm going to do subtraction. So if the full thing is 17.5 and this is x, then this is 17.5 minus x. Okay, I'm actually going to start with that expression to write my proportion. So 17.5 minus x. I'm going to go inward so I get both of those sections. So that would be over x. Then I'm going to go in out again over here, so 8 over 6. And then I cross multiply. 17.5 times 6 is 105. So 105 minus 6x equals 8x. Going to add that over. 14. And then divide. I get 7.5. Okay. Next one over here is another nested diagram. We only have two parallel lines this time, so we have a small triangle and then a big triangle. This one's actually nice. We're going to redraw them, but they've actually given us all the information we need already to make it pretty straightforward. So we have the small one and the big one. I did not do a good job. Dun, dun, dun. There we go. So the small triangle is 4 and 3. And then this side right here is 4 plus 6, that's 10. And then, interestingly, they've given us this bracket here. So they're going from end to end, so this entire segment is x. Please do not do x plus 3. This bracket indicates that the 3 has already been included in this expression right here as x. So if you add the 3, you're double counting a 3. It's 3 more than it actually should be. So just pretend that's not there, because the bracket's already telling you what the full length is. So now I have everything set up, so it's going to be x over 3 equals 10 over 4, because we like to start with the variable. And then we cross multiply. 7.5 again. Excuse me. Okay. This last one here is another example of similar triangles, very similar to the first one. We have our alternate interior. We also have alternate interior up here if you wanted to include those. We also have our vertical angles that are congruent, so similar by angle. So we're going to use those relationships to figure out what sides are corresponding so that we can write our proportion. So I'm going to start with the variable expression, and then the side that corresponds to that is the 13, using the markings that I just added with the angles. Then I go back to this triangle. Now, notice in this triangle on the left, I have 2 sides labeled, but in this one I only have, I have 3, all 3 sides labeled, but in this one I only have 2. So you need to be careful that the next side you use has to have a corresponding side in this triangle. If I were to use the 32, I would not be able to complete the proportion because I don't have a corresponding side. So I'm going to ignore that. I'm going to use the 45 and the 20 because those correspond. 45 and 20. So I cross multiply. And we have a relatively large number here. 585. So you're going to go ahead and subtract 40 and then divide by 20. And you get 27.25. Okay, so that's your cumulative review for all the different ways that we've learned to solve. Of course, there are other ways that we saw solving. There were situations where there were radicals that you need to simplify, or factoring where you need to check, so all that still applies. But this is just a general review of the process that you would use. All right, now we're going to finish with a proof. So any of the rules that we've learned so far could be utilized in a proof to show that something is true. Now, if you take a look at this proof, we know that ZY bisects this angle, so we have the congruency marks, and then we know XW is congruent to YW. Now, we're trying to prove that YZ is congruent to XZ. Typically, when you see something like that, we have these congruent angles, we have these congruent sides, and you're trying to prove other things are congruent. The first thing that should come to your mind is proving that the triangles are congruent and then using CP/CTC, right? But if you look really carefully, the only piece of information that I could add would be the reflexive property right here. But in each triangle, that would give me angle side side, which is not, or side side angle. So I can actually write it without getting in trouble. This rule doesn't work for us. Remember, that was an invalid rule. So there's actually no way that we can prove the triangle's congruent to use that shortcut. If we had more information, like these were perpendicular, that would definitely be a great shortcut to saying that, oh, the triangle, this is congruent to that triangle, so I can use CP/CTC. But we don't have that. So you have to try a different method. Specifically the fact that we have an angle bisector. We know the definition of an angle bisector cuts these two angles in half, but we've also learned something new about information we can get from the fact it's an angle bisector. So I'm going to go ahead and just write that down really quickly. ZW, but okay, I should be typing this. I'm not going to be able to add the symbols in, so just bear with me. Hold on. There we go. ZW bisects XZY. You guys should include the symbols. I just can't get that with my keyboard. All right, so obviously that's your first step, the first given. Now I'm not going to write both givens in the same line or together because I kind of want to use them separately so we can see how we use them one at a time to go through a proof. So if all I know currently is that this is an angle bisector, we learned something new about that in terms of proportions. So what I'm going to say next is using the proportion rule from the angle bisector. I can say that this over this equals that over that. That's what we learned, right? Or, well, you could write it however you want to, but I'm just going to write it that way, going from here to here and then here to here. So that would be YW, I have to write small to get this to work, YW over YZ is equal to, so that was this over this, is going to be equal to XW over XZ. And let me just double check the name of that rule. Yeah, triangle angle bisector theorem. That's how we got that. I'm going to type that just so it's faster. So the triangle angle bisector theorem. Right? That's what allows us to say that those sections are proportional. That's something else that we've learned now that we have been talking about proportions. All right, cool. So we have that part. Usually when we have proportions, right, we're trying to get a congruency here, or an equality between those two segment measures. So what I'm going to do is, instead of keeping it in fractions, I kind of want it to be linear so I can work a little bit more easily with this, because obviously we don't like fractions. So in order to kind of adjust this so it's more linear instead of fraction, I'm going to go ahead and cross multiply. So I'm going to have that YW times XZ, and I'm just going to use parentheses to separate them so we don't get the letters jumbled up. So YW times XZ is equal to YZ times XW. And you can just say cross multiply. Should have typed that. Okay. Excuse me. All right, so now that we have that, we've done everything that I could with the fact that it was an angle bisector, and we kind of adjusted the way that the equation was written. Now I'm going to bring in the next given. Okay, so I'm going to type that. All right, the next given tells us that XW is equal to YW. Right, that was our other given. So now I'm going to move forward with that idea. I can take that idea that these two are equal and kind of adjust this equation I just wrote up here. So XW, which I have here, is equal to YW. So remember, whenever we see something like that, we always use the substitution method to help us out. So what I'm going to do is I'm going to take either XW and plug it in for the YW, or take YW and plug it in for the XW. It's really your choice of what you want to do. I'm going to go ahead and just switch out the YW for an XW because that's easier for me right now just to write the first one differently. But again, you guys can switch out whatever you want. So I'm going to switch out the YW because I know it's equal to that. I'm only going to do it for the one though, because my reasoning right now, just let me finish writing this, hold on. Remember, we're trying to get just YZ and XZ alone. So in order to do that, it would be nice to have those two be the same so I could divide them away, right? So you're only going to substitute one in so that now they're the same, one on each side of the equal sign. So it would kind of be counterproductive to switch this one to an XW and that one to a YW. You would have done no change. So just change one, and then remember that's the substitution method. Because I know they're equal, I can switch it out. Substitution property, really. Okay, so now what happens when I did that, I have the same value on both sides of the equal sign, so I can actually divide that away using the division property, leaving me with just the two sides that I wanted. Okay, and it doesn't matter, they're in a different order, whatever. You can either write it like this, or you can just go ahead and switch the order right now if you want to. I am not really that picky, it's okay. You're saying the same thing, that those segments are equal in length. Right, so when you divide those two away, you get exactly what you were looking for, and that is the division property. Okay, there you go. That's the proof using the triangle angle bisector theorem. So make sure you keep that in your back pocket anytime you see a triangle bisector. It doesn't just split the angles into two equal parts. You can also apply the proportion if it's going to come in handy.